Okay, let's work on this problem. Now, this is one I don't know the reactions right off the top of my head, so we're going to have to solve for the reactions first. So I'm going to go ahead and draw in the positive shear at A and the positive shear at B. And then I'm going to have to go solve for those. So to do it, I'm going to sum moments about B. You could sum moments about A, doesn't matter. So summing moments about B, what do I have? I have this moment. Remember, I'm using right-hand rule, so this moment is then negative. That's 4,000 pound-feet. The 600-pound force about B creates positive moment, and it has a moment arm of 10 feet. Then the positive shear at A creates negative moment with a moment arm of 20 feet. So what is the shear at A? Looks like 200, 100? What do you get? Somebody help me with the calculator. This is 4,000 plus 6,000 is 2,000. It should be 100. No, it should be negative? Yeah. No, I got positive 100. Anybody else get that?
Yeah.
So that's 100 pounds. And then if I sum forces in the y direction, I have my shear at A up, my shear at B is down, and I have my minus 600 pounds. So the shear at B should be minus 500. Is that right?
Hey, why would it not be negative 100?
Which one?
For moment of B. You have
This is not moment, this is the shear.
I mean, the shear of the moment around B. The shear of it. You got 6,000 and negative 4,000.
Because BA is a negative, so you have to times everything by -1.
Oh, duh. Yeah, okay. I was doing negative 2,000 in my head.
So everybody's happy with the 100? How about this one, the minus 500?
Yeah, I got it. Okay.
Okay. So now I'm going to pencil in my template. So there's the edge of my beam. We know something's going to happen here at this 600, so I'll pencil that in. And we know something's going to happen here because I got that jump in the moment, so I'll pencil that line in. Then I'll come back and add my positive X and say that's going to be my shear, and all my shear will have units of pounds. Okay? So let's start with the shear diagram. What's the shear on the left side? That'll be the shear at A, and it's 100. Now, if everything goes well, I should end up with the shear over here at B equal to minus 500. Let's see if we can make it work. So we know that the change in shear is the area under the load diagram. So over the first 10 feet, what's the area under the load diagram? 0, so no change. So I should stay at 100. I also know the slope of the shear diagram is equal to the load. And what's the load here? 0, so I have a 0 slope curve. So it looks like I have constant shear over the first 10 feet of positive 100. Now, as I go from the left side to the right side and pass under that 600-pound force, what happens to my shear? It changes by 600 pounds, and it's negative. So I should hit minus 500. Now, let's look at the last 10 feet. It says the change in shear is equal to the load. What's the load over the first 10 feet? Last 10 feet? 0. So there's no change. So that's great. Minus 500 plus 0 is 500 minus 500. So that matches. And the slope is the load, and the load is 0. There's my shear diagram. Maximum shear in the beam, minus 500 pounds. And it occurs anywhere on the last half. That looks pretty good. So let's do our moment now. So I'll draw a positive x-axis for the moment. And the units for moment will be in pound-feet. Now what do I know about the moment? What's the moment at A? 0. What's the moment at B? 0. So I better make those match. I also know that the change in moment is the area under the shear diagram. Well, there's a nice little area of the shear diagram with the first 10 feet. What's the area under that shear diagram? Yeah, it's 10 feet times 100 or 1,000, and that's positive, right? So 0 plus 1,000 brings me to 1,000. The slope of the moment diagram in that section is equal to the shear. So what's the shear over the first 10 feet? Positive, and it's constant. So if I actually wrote that in, that would have a slope of positive 100 to 1. Okay? Now I can't just go ahead and do all of that, the area of the shear diagram, and add it to here because I've got a point. So with that, I'm just going to look at first just the first area. So I'll kind of sketch that in like that. Now that's going to be negative, right? How much is that? 500 times 5 is minus 2,500. So if I'm at 1,000, well, I don't have this to scale at all, do I? So if I have this 1,000 and I subtract 2,500, what do I get? Let me extend this a little bit and say I get all the way down to minus 1,500. So far, so good? What's the slope between these 2 points? Well, it should be equal to the shear, and the shear is constant, and it's negative. In fact, if I look at this one, it should be minus 500 to 1. Now, I don't really care right now where the moment crosses the 0 axis, so don't concern yourself with that yet. Now, what happens is I go from 15 to 15.1 billionth. I have a clockwise applied moment of 4,000. So from negative 1,500, I add 4,000, which brings me up to 2,500. Then I can deal with the second part of this, and the area on the last 5 feet, area of the curve, is, again, minus 500 times 5, which is minus 2,500. So 2,500 minus 2,500 is 0, and I get the same thing. And although this is not perfectly to scale, my slope is also minus 500 to 1. So these two slopes are the same. They just shot up. So now, where's the maximum moment? And what is the value? Right, it's 2,500, and it occurs 15 feet from A. So if you were designing this beam, you'd worry mostly about the maximum moment. Now there would be a negative moment. Depending on what material you use, you might have to worry about that.
Would you also feel like a safety factor around 3,000, or is that about enough?
Well, we're just doing analysis. So we're assuming these loads are already accounted for safety. They've been factored up. When you guys take your design courses, you'll get actual loads that you'll have to apply load factors to increase them. And then you'll also take whatever the strength of your beam is and reduce it. So it's a double layer. You apply more loads than you really think are there, and you assume your structure is actually weaker than it actually is. That's the level of conservation that we do. So any questions about that? Mr. Carter?
Why did you add 4,000 instead of subtract?
Well, the rule says clockwise moments create positive jumps. Now, if we would have tried to subtract 4,000, what would have happened? We'd have gone down to minus 5,500, and then we would have changed the moment again another negative 2,500. We'd have been down to negative 7,000 moment at a pin. Can you have a negative anything at a pin? Out right at this point, no. So that should tell you that you made the wrong choice.
So, do they say clockwise?
The rule is clockwise applied moments create positive.
Is that because the bending moment is the same?
Any questions about that? Okay.